there, I'm Alex Plum. My talk is on autocatalytic chemical ecosystems in spatial settings. So I wanted to start with this quote from the French naturalist Georges Cuvier. I don't think it's a good definition of life, but I think it captures one feature of life that's very important, specifically this feature of autocatalysis, which I think is the central motif for self-propagation that we see kind of all across life and that may have been relevant in life's earliest stages. So we say that a process is autocatalytic if the products of that process catalyze the process itself. Here I'm going to be talking about autocatalytic cycles, where you have a sequence of reactions that form a cycle, such that with every turn of the cycle, you get a stoichiometric increase in the number of some set of chemicals that we'll call member chemicals. You can take all of the chemicals involved in an autocatalytic cycle and partition them into food chemicals, into member chemicals, and into waste chemicals based on which sides of the reactions they show up in. And so here's a simple example where you just have two reversible reactions. You have two member chemicals, M1 and M2. You have one food that's being used for both reactions and one waste chemical. And in principle, these can be irreversible. Here I've drawn them as reversible. And because they're reversible, you can drive them in either direction. If you have an abundance of food, they can be driven in the productive direction that provides the stoichiometric increase in the member chemicals, allowing them to self-propagate. But if instead you have an accumulation of waste, it can kind of wind down in the other direction, and you can get a stoichiometric decrease in the number of member chemicals as well. So we've analogized these autocatalytic cycles to biological species, in part because they're consuming food, they're producing waste and self-propagating themselves, and we've demonstrated that they can exhibit logistic growth. If you put them in a closed reactor, some amount of food available, some seed member species, they can start growing and they can reach equilibrium concentrations. But this isn't of great interest in an origins of life context because life is an out of equilibrium process. So in practice, we typically simulate these cycles in chemostats, wherein you have an inflow of food from a source that drives them in the productive or autocatalytic direction, and where everything is diluted out of the system. And this has two implications. One, it helps to offload the waste to kind of keep it from being driven in the other direction. And it also provides a selective pressure so that now if the cycle doesn't replicate or propagate its member species quickly enough, they'll just be diluted out of the reactor. So it's not trivial that these cycles are going to persist anymore. Persistence becomes a problem, something that they have to kind of achieve. So when you simulate these, you can get time series that looks like this plot over here, where you have a depletion of food through time, you have logistic growth in the concentrations of member chemicals here in blue, and you also have a buildup of waste. You can choose to simulate them using ordinary differential equations if you're in a well-mixed reactor, and that assumes that you have large enough quantities that you can treat continuous concentrations of chemicals. The other approach is to simulate things stochastically, and in kind of the large N limit, this looks very similar to the continuous case, but as you go to smaller and smaller numbers of chemicals, things look a lot noisier, and you can start to have more contingency in the dynamics, where you can have the stochastic loss of a single chemical or the stochastic dispersal of a single chemical in a new location, changing the dynamic somewhere else. And so in everything I show here, I'll be taking this stochastic approach. So that's all the dynamics for a single cycle. We're ultimately interested in combining different cycles and seeing how they interact ecologically. So here I show the member chemical concentrations over time, or counts over time, for the different autocatalytic cycles shown on the left here. They can exhibit competitive exclusion, competitive coexistence when they share a common food source. They can also exhibit mutualisms, wherein the food or the waste of one chemical serves as food for another autocatalytic cycle. They can also exhibit predation, wherein the member chemicals of one cycle serve as the food for another cycle. And the dynamics resemble those that you get in the Lotka-Volterra equations in ecology, where you can get both stable and damped oscillations, predator or prey dominance, or coexistence of the predator and prey. And you can also get priority effects, wherein two cycles might mutually inhibit one another, so that it matters if one cycle gets seated in a location first versus the other, since they'll suppress the growth of the other cycle. So why is this relevant to the origin of life? We think that these autocatalytic cycles provide one of the simplest ways, in the absence of needing compartments or polymer genetics, to get this sort of self-propagation that you see in metabolism. And we think that they can provide an avenue for the accumulation of complexity to ultimately serve as precursors or scaffolds for later stages in the origin of life. So as an avenue for kind of increasing the chemical diversity that you might need to achieve later stages. And we think that you can do that by taking individual cycles, composing them through various ecological interactions, and then using the sorts of avenues that we see in ecology for the accumulation of complexity. So how do you accumulate complexity in ecology? One way is through ecological succession, wherein you have some species that lay the groundwork for others to later succeed them. You can imagine this in a chemical context where the waste or member chemicals enable the activation of new cycles that couldn't have been activated until those first cycles were activated. You also have ideas in ecology about how to maximize biodiversity, for example, through the intermediate disturbance hypothesis. And finally, you have ideas about how spatial structure can be relevant to the accumulation of complexity in ecosystems, where you have meta-ecosystems and diversity among them, and migration between them that allows for recombination and the formation of new ecological states. So in an origins of life context, we often think about these chemical ecosystems as persisting in spatially structured environment like adsorptive mineral surfaces, moving across those surfaces where they're effectively concentrated, where their diffusion is effectively lowered. And those different ecosystems might interact. When they interact, they might annihilate, they might continue to coexist, they might fuse and modify one another. And so we wanted to understand how these chemical ecosystems behave in space. So the earlier kind of ecological time series that I showed you were all in well-mixed reactors. Now we're going to consider these systems in space. So here's an example where a cycle is seated in the center and diffuses outwards, kind of spreading to new sources of food. And of course, we know that spatial dynamics are important for autocatalytic chemical systems. We have classic examples like the Belousov-Zhabotinsky reaction. It's out of equilibrium process. We know that they can form stable patterns. So I want to consider cases where cycles mutually inhibit one another, because getting more complex ecosystems is easy when there are mutualisms between the cycles. It's hard when you have inhibition between them. And there are various ways that cycles can inhibit one another. For example, you can have the waste of one cycle interfere with the food of another cycle, or you can have their member species annihilate in a much simpler example that I show in the bottom. This is the one that I'm going to be working with in the subsequent slides. So you can put these in space. Here I have a hexagonal lattice with chemicals reacting within each site and diffusing between sites. And I'm coloring them according to the fraction of member species that belong to one of these two mutually inhibiting cycles, red for cycle A, blue for cycle B. And with slow diffusion, they stop interacting and just form these stable patches. With much higher diffusion, you can see one cycle starts to crowd the other out globally. And we can look at this more systematically, varying the diffusion of all the chemicals involved, kind of gradually increasing. In the low diffusion case, you end up with pretty randomly distributed ecological outcomes. In the very high case, you end up with one global winner, one cycle driving the other extinct. And you can look at the heterogeneity of chemicals across this hexagonal lattice. And what we find is that in the intermediate diffusion regimes, this heterogeneity is maximized. And insofar as these cycles are inhibiting one another through these reactions that might produce other chemicals that could help to provide support for the activation of future cycles, you don't have that sort of interaction in the very, very low diffusion case, and you also lose it in the high diffusion case when one cycle is driven extinct. And so this suggests that some intermediate diffusion regimes are the most favorable to kind of this biodiversity, so to speak, of these chemical ecosystems. That's all with keeping these cycles on an equal playing field where they have the same reaction kinetics and the same diffusion properties. What I want to show next is when you vary the properties of these two cycles asymmetrically. So I'm showing time series here on the right of both cycles being seated in some central site in a 3x3 array, and they can diffuse outwards. I make cycle A in red fiercer so that it consumes food more quickly than cycle B. And because of that, it starts to drive cycle B extinct initially. But cycle B is made faster than cycle A, meaning that it can diffuse outward more quickly and access new sources of food. And so despite initially being driven down, it manages to dominate in these outer sites and eventually reinvade, so that in the long term, it ends up driving cycle A extinct. And you can kind of vary these properties systematically and construct a phase diagram. Here I vary the relative fierceness and relative fastness of the two cycles. And you find regimes in which either of the cycles can be favored, suggesting that spatial environments can select for new types of traits, such as the diffusivity of these member chemicals, once you put them in a spatial environment. A well-mixed reactor would be blind to these sorts of traits. Notably, you can also look at other types of inhibition that don't involve explicit chemistry. You can look at competition for adsorption sites on mineral surfaces, and there we find very similar dynamics. And I think that this is suggestive that something like the intermediate disturbance hypothesis might hold even for these chemical ecosystems. And of course, in an origins of life context, there are lots of different types of disturbances that you could have. The noise of the spatially structured environment that you have, different impacts And so with that, I'd like to acknowledge David Baum, my undergraduate advisor at the University of Wisconsin-Madison, and Chris Kempis, my mentor and collaborator at the Santa Fe Institute, some excellent grad students and postdocs, including Profil, who just defended his thesis last week, and some excellent undergrads that I've had the opportunity to work with, including Gage, actually. He should be on here. All right, with that, I'll take any questions. If there's time. Okay.
Also, if everyone just wants to give their name and affiliation and ask a question, that'd be great.
Hi, my name's George Scheibel. I'm from Montana State University. And I should preface I am a microbiologist. So, but that was a great talk. I thought you did a good job breaking it down for us. I'm just curious, when diffusion happens, I think of it in like three-dimensional space. So you were showing a lot of two-dimensional graphs. So what does that look like in three-dimensional space? Yeah,
so I didn't do simulations in three-dimensional space, in part because I think the most origins of life relevant spatial structures are going to be these two-dimensional environments. I think the two-dimensional environments can help to constrain kind of the effective diffusion that you would have. They can concentrate chemistry. Lots of origins of life theories that look at adsorptive mineral surfaces already. So we were kind of committed to that sort of scenario. And here, the idea of intermediate diffusion being favorable for chemical diversity, I think that's further support that's the type of scenario that might be important. I think there's a quote from Günter Wasserschauser, who kind of pioneered some of these ideas, that we don't build planes in the sky, we build them on the ground, and that's for a reason.
Just to follow up with that, what kind of mineral surface would you consider this happening?
Yeah, so kind of the experimental side of my group in undergrad, we were using pyrite surfaces, but here we're chemically agnostic, and we're also agnostic to the exact type of mineral surface.
Hi, I'm Ellie. I'm from CU Boulder. And I was wondering, so I'm mainly a lab chemist, and I was curious if you had any personal thoughts of how you would want a chemist to do some of this work, or what kind of questions you would want a lab chemist to do to help ground truth some of the modeling work that you do. Because I work a lot of mineral absorption and mineral facilitated chemistry, and of course when we do a lot of this stuff, it is an equilibrium reaction, because you're kind of waiting for it to resolve to equilibrium. We're basing our reactions on that. So how would you kind of design something like this, or theorize, or hope for something?
Right. So a lot of what I showed, that in the well-mixed cases, we were working with chemostats, and certainly chemostats are an experimentally kind of realizable approach. There's another side to our group that looked for kind of real autocatalytic cycles and known chemical reaction networks, both biotic and abiotic. And so I think one promising approach is to look at how these chemical ecosystems might explore that space where you seed with one chemical that activates maybe a single cycle or a small set of cycles, and then through the addition of subsequent seeds, you might activate kind of new cycles. And so I think there are kind of experimental approaches that can be done there, and I think people in our group are continuing that.
Okay, hello. We have a question from online, actually. So this comes from user Alex. He's asking, can you simulate tipping points hysteresis spatially with this method?
Tipping points. It's hard to ask for a clarification via Zoom.
Okay, Alex, if you can hear this, please clarify your question and we'll come back to you. Thanks.
Okay.
Hi, I'm Jake from UCSD. Can you clarify why you used a stochastic process instead of just solving differential equations analytically?
Yeah, so you can have cases in these chemical ecosystems where there's kind of some unstable fixed point. And those unstable fixed points, you need some degree of stochasticity to break out of them. So that's one reason. If I just use deterministic simulations, you could get stuck in those. It's also the case that in ecology, we're interested in lots of contingency. And stochasticity, and then doing lots of replicates allows you to explore all those contingent outcomes. That's largely the reason.
Okay, we have time for one more question.
Hi, I'm Dana from Indiana University. I'm an ecologist by training, and it was really interesting to see all of those theories that I've been trained for in this context. as ecologists, we abandoned intermediate disturbance hypothesis because we haven't observed in nature for 20 years. I was wondering if there are ways to test experimentally. What do you think about that? And also a clarification for tipping points. I think the online person mentioned you can probably see the signals before transitions, like increasing time autocorrelation or coefficient of variation. And so on.
Yeah, absolutely. Thank you for the question. Yeah, so I think in ecology, the intermediate disturbance hypothesis is controversial, and many people have abandoned it. I think in this kind of modeling context, it's very easy to kind of look for it, just because we're doing experiments in silico. And I think that if it does hold in the biological case, certainly it holds in the chemical case. There's a possibility that it holds in the chemical case and not the biological case. I think the weak version of this is that there are certain types of disturbance regimes that can be beneficial for chemical diversity, even if the intermediate disturbance hypothesis doesn't hold writ large. To the tipping points question, I think you do see sort of kind of signs. In the diffusion cases, I kind of vary it. You end up seeing sort of power law scaling in the patch size, sort of like you would see in an icing model in physics. And so the sort of theory that looks at tipping points there would also apply here.
Thank you very much, Alex.